Good afternoon. My name is Sedigheh, and today I'm very excited to present my recent work on optical image processing with metasurfaces. Our metasurfaces can process images not only in spatial domain, but also in the temporal domain. And this work enables event detection for neuromorphic computing. And I'm going to tell you in a moment what that means and how we can achieve this functionality at zero energy cost, very high speed, and simply by nano patterning a thin film of silicon. So let's start by looking at how conventional frame-based digital imaging works. I'm going to show you a short movie. And consider this movie as the input scene for a frame-based camera. There are some interesting events happening in the movie. The lightning bolt suddenly appeared and disappeared, and there's this flying object emerging from nowhere and moving around for a while, and then it suddenly vanishes. And I've extracted the important frames here so we can make a comparison between the input and output clearly. So in the frame-based imaging, we take pictures of the scene at constant time intervals. And that already implies that we have some time delay, and we are also limited in temporal resolution. Then we process these images to recognize the relevant object, and digital processing requires analog to digital and digital to analog converters, which are bulky, energy consuming, and they require large amounts of memory. So what might happen in frame-based imaging is the following. We completely lost the lightning bolt, and there's a time delay. So let's remove this analog to digital conversions, and recent works on the concept of metamaterials and metasurfaces have been showing that maybe it is possible to perform mathematical operations on the spatial distribution of an incoming image. So if we do differentiation on a spatial profile of an image, then we can transmit only the edges of that image. And that means we can reduce the energy consumption and the memory requirements. And we can improve the resolution in time and space. So how about using a thin subwavelength metasurface, which is passive and it works at the speed of light? So this metasurface needs to take spatial derivative. It means that we should engineer the dispersion of this metasurface in a way that it filters out all the low transverse momentum components of the image, which are the slowly varying portions of the image, and then it should transmit the high momenta, which are the edges. So, and my colleagues at CUNY have recently achieved this. So we can see that the transverse K-vector is not transmitted, and as the angle of incidence increases, the transmission increases. And this is how we can realize a spatial differentiation on an image. If we look at the dispersion in the omega K space, this is the kind of dispersion that we need to engineer to have edge detection. And what we here did, we engineered the non-local response of the metasurface in the space. There has been several groups that have been working on optical image processing and in particular edge detection. And they've been trying to improve different figures of merit for various applications. And there have been lots of very exciting experimental demonstrations. Now, let's go back to our movie and see what happens if we apply an edge detection metasurface to our imaging system. So you can see we lose nothing. And with much cleaner images, we can improve the resolution in time and space, and we can reduce the energy consumption and memory requirements. But can we do even better than that? Our vision tends to ignore static images, and instead it's turned on when the scene changes. There's been lots of work recently around neuromorphic computing, which tries to create hardware and software that mimic the way our brain works. In the movie that we saw, the Empire State Building is always there, and we don't care about it. What we care about are the events, when the lightning bolt starts, when it ends, when the weird flying object appears, how does it move, and when it disappears. And we want our metasurface to see things that we want to see and remember. And interestingly, to do that, we not only need to do edge detection in space, but also we need to do edge detection in time. It means that the metasurface that we need to design should take, at the same time, spatial derivative and temporal derivative of the scene. Similar to engineering the non-locality in space, which was tailoring the dispersion versus the angle of incidence, now we also need to engineer the non-locality in time, which is tailoring the frequency dispersion. And we need zero transmission here at center frequency and increased transmission over the bandwidth. And combining these two responses, this is the kind of dispersion that we need to do event-based edge detection. But is it possible to engineer non-locality in both space and time? It is not trivial, but I will show you that it is actually possible. So this is an intuitive approach that we followed. We know very well how to do edge detection in space. We can design this metasurface to do edge detection. We have lots of experience in it. And we also know theoretically how to do edge detection in time. And we designed this metasurface for that, and this is the transfer function. Now, perfect. We have everything. Let's cascade these two metasurfaces. And of course, it will not work just out of the box. There are some back and forth reflections, and there are frequency shifts that we should take care of by fine-tuning the geometry. And after fine-tuning the geometry and optimization, this was the transfer function that we got. And this is reasonably close to the ideal case that we were looking for. To see how close this is to the ideal transfer function, we can write this transfer function as a summation of different terms, each one corresponding to a derivative. We have a DC background here, first and second order derivative in space and in time, and these spatiotemporal terms. So our transfer function, remarkably, 93% it does, it's equal to second order derivative in both time and space. But the contribution of the other spatiotemporal terms will not hurt. So we can claim that overall it does 98% spatiotemporal differentiation. Here I want to stress that this is a thin subwavelength film of silicon, nano pattern. The thickness, the overall thickness is less than 1 micrometer, and it's completely passive, and it's doing event-based edge detection. So now let's test the performance with some scenarios. In the first scenario, we have 3 strips, 1D strips. This is the space axis, and the strips are being turned on and off in time. This is the time axis. What we expect to see as the output of the metasurface is that we want to see the edges of the strips only when there is a change in time. And that is the spatiotemporal corners. So here is, this is the output of the metasurface, and this is the exact mathematical operation. Here we can see some fade, spatial only and temporal only edges. But we can compare the output intensity in the temporal and spatial cross-sections. And we can see that the intensity of the spatio-temporal corners are very well, they can be distinguished from the undesired background. And this is because our transfer function is not 100% ideal. In the next scenario, again, we have a 1D strip. After a while, the width of the strip starts to change. And we expect to see the edges of the strip only when the width is changing. And this is the output from the metasurface, and this is from the exact mathematical operation. In the third scenario, now we want to look more carefully at the intensity of the output. So we have, again, the same 1D strip. After a while, it starts moving at a constant speed. We tried here 3 constant speeds. And then it undergoes an acceleration, and eventually it stops moving. Here's the output. We can see in the output that the intensity, the output intensity at some certain velocity is the highest. And we refer to that velocity V0. So where this V0 comes from and why this happens, if we take the Fourier transform of each section with constant velocity, it's mainly a line in the omega k space, and a line in the omega k space passing through the center, well, it defines a velocity. And exactly at V0, this Fourier transform aligns with the high transmission corners of the transfer function. And that's why we get the highest output intensity at V0. This V0 is a property of the metasurface. How? And it can be found from the transfer function. The highest spatial frequency that the metasurface can process is called numerical aperture. We can define a temporal numerical aperture similarly by this bandwidth. And this V0 will be proportional to the ratio of the temporal and the spatial bandwidth here, to temporal numerical apertures here. And by controlling the numerical apertures, we can control this optimal effective velocity that metasurface captures. We've been trying to do experiments. Spatial edge detection, we very well know how to do it, and we have lots of experience in it. So we tried the temporal edge detection. This is a metasurface that we designed and fabricated. And this is the amplitude and the phase of the transfer function. This phase jump is telling us that the metasurface is doing first-order derivative in time. And this is the transmission that we measured in the lab. And we tried some different inputs. And in each case, we can see a nice first-order derivative in time and the edges. Then we tried the idea of cascading two of these metasurfaces. And here you can see the response of each metasurface doing first-order derivative in time. And when cascading them, here we get a nice second-order derivative of the output. And right now we are working on doing the spatio-temporal experiment. So far, from digital frame-based imaging and then analog optical imaging, we are moving to event-based analog optical imaging with metasurfaces, no energy cost, completely passive at the speed of light. And of course, there's a lot more to explore both on the theory side and the experiment side. But however, all I talked about so far was in infrared and visible wavelengths. What if we want to apply the same concept to radio waves? And the applications to radio frequencies can be very exciting. This opportunity of engineering the dispersion both in space and time at a larger scale on metal-based metasurfaces with more complex designs, and applying event detection for more sophisticated applications like seeing through the dark or beyond the wall, or for biomedical applications. And there's been lots of work recently on RF imaging and many applications like hand gesture recognition or silent speech recognition. And they can benefit from these types of analog-based processing in space and time. We can monitor our heartbeat by using millimeter wave radar sensor, and for example, and most of these applications, they are based on machine learning techniques and neural network analysis. And our approach is not only limited to doing derivatives on an image in space and time. We can perform arbitrary mathematical operations, and these applications can benefit from that. And I want to thank first and most my advisor, Professor Andrea, also Michele, Cotrufo, and Dmitriy Korobkin. They helped me a lot. I cannot thank them enough. And of course, thank you for your attention. And I'll be back to answer any questions.
We have 4 minutes for questions. Please use the mics.
No question?
Go ahead. Can you use the mic?
Does it matter how fast the object is moving?
And that's a very good question. I talked about the optimal velocity that the metasurface can capture. And that optimal velocity in the metasurface at optical frequencies is very high. But it's true that that optimal speed is very high. But at lower speed, we still have a good output intensity. And we still have a good contrast between the background and the intensity of the spatiotemporal edges that we want.
Other questions? Go ahead.
Your work was based on the surface for edge detection, but have you considered like blurring correction, like image correction?
Of course, that approach, we were trying to, we know how to engineer non-locality in space. We were trying to engineer the non-locality in time. We tried derivatives. Of course, we can try integration and blurring.
Any other questions? Go ahead.
Maybe this is a basic question, but what exactly do you mean by non-locality? I guess in this context, I don't understand that.
We have local and non-local metasurfaces. By non-local metasurfaces, we mean that the overall response of the metasurface, like here we have a grating, and it's not only the different response from different resonators that they perform separately from each other.
I see. Thank you.
Any other questions? Yes.
But can you comment on the imaging resolutions compared with other conventional methods?
This is very important because it was one of the main motivations of this work. Well, in the frame-based imaging, of course, we have limited resolution in time. And with this event-based imaging, I can say that we have no limitation, no temporal resolution limitations, because it captures the event at the speed of light. And with the spatial resolution, it depends on the numerical aperture of the metasurface. If we can design a metasurface with a wider spatial numerical aperture, then we get better spatial resolutions.
Thank you so much. We'll move on to the next one. We're good?
All right. Well, I am very excited to talk to you all about my work on detecting meteors in high-power radar data using a convolutional neural network that is trained on synthetic radar data. So why are meteors entering Earth's atmosphere so fascinating? And I should clarify that I'm talking about very tiny particles that are constantly entering Earth's atmosphere on the daily, not big meteors. Well, we can use what we see on the radar of these meteors to determine properties of these particles, such as their mass and density, and also that the orbit that they come from. We can also use these meteoroids and their meteor signatures to determine properties of the atmosphere that they enter. So density and winds at altitudes that are very hard to observe otherwise. And then also we can quantify the hazard that these particles pose due to hypervelocity impact collisions between these particles and spacecraft. So they can cause mechanical damage, as is the case for James Webb with the mirror, and then also electrical damage, which happens when a plasma forms that then emits radio frequency waves that can interfere with the spacecraft electronics. So there's a few different methods of observing meteors. You can use a specular meteor radar, where you reflect radio waves off of the meteor trail. It transmits kilowatts of power. There's high-power large aperture radar, which transmits megawatts of power to get much more fine-grained observations in multiple different meteor signatures. And then you can use optical instruments, and I have a video from Peter Brown's group. They can observe the entire sky or use mirrors to track the meteor, and they observe slightly larger particles, like milligram scale, whereas the radars tend to observe microgram scale particles. We will focus on high-power large aperture results and using machine learning on that. So high-power large aperture radar facilities generate terabytes of data. Vast data sets like this diagram here is just a few seconds of data. And so this is an RTI plot. On the x-axis is time, and then on the y-axis is altitude. And the meteor head echoes are these streaks that you can see circled. One of them is more obvious here, but then some of these other ones really blend in with some of the background phenomena. This here is the equatorial electrojet, which happens at Hikamarka, and then you can also have non-specular trail echoes, such as this one in the lower right, which occurs due to incoherent scatter when your beam is perpendicular to the magnetic field, as is the case often at equatorial radars that are pointed directly up. You can also have specular trail echoes, which don't show up in this diagram, however, they can show up at any meteor radar. And we're interested in the head echoes because they allow us to learn the most about these particles as they're entering Earth's atmosphere. They're a direct result of that signature. And so they help us with the broader motivation of this work and kind of the scientific goals. So we need to talk more specifically about how head echoes form in radar data. So you have your HPLA radar facility that is transmitting pulse after pulse after pulse. These are coded pulses at a co-located facility transmitting and receiving, and the beam tends to be very thin, so on the order of 1 degree. And you have your plasma that surrounds the meteoroid as it enters Earth's atmosphere, and it reflects the radio waves that are being transmitted and on multiple subsequent pulses as the meteoroid descends. And so as it descends, then you'll have some range rate or the velocity along the beam, and that range rate can be determined via the Doppler shift in your raw data. This is a range time intensity plot of the raw data. The altitude aliasing is due to the fact that it is a long coded pulse with some finite length in time and therefore in altitude. And you can decode the image using a matched filter to then clean it up into this nice streak that shows the exact altitude that that meteor has been observed at. So that is the head echo. Why is head echo detection hard? Well, I sort of touched on this in the prior diagram where you could see that some of those signatures were blending in with background phenomena. You can also have objects that look a lot like head echoes, such as satellites or aircraft. Sometimes they'll be obscured by the equatorial electrojet or other phenomena or clutter. And then sometimes there will be non-specular trails, which are also meteors, but then here in the raw data, you can't even see the head echo signature. You can only see it after a matched filter, and then it's a little bit broken up. And then you can also just have radar clutter that sort of gets in the way, and here also the head echo is not really visible in raw data. So you can't just look for high strength signals or streaks. You have to kind of look more carefully for these head echoes and know where to look for them, and that's where machine learning becomes very useful. So machine learning in the past has been used to detect head echoes. Felix Lee published in 2022 a paper on using feature extraction and then a convolutional neural network. Upsides to this is you get very good sensitivity and precision, so generally a good method. It identifies bounding boxes for the head echoes, but it is computationally expensive and also requires manual labeling of many radar images. And once the method is trained, it only works at the same facility that you've trained it at and same experiment parameters. Then in 2023, he published a similar method, very similar pros and cons here, but many, many manual labels necessary of head echoes to train the neural network. This would take weeks or months, and we want to avoid that. So my method will address all of these kind of downsides to the prior work while also being similar in what it does well. So in order to do machine learning, we need to have some data. So we perform 4 hours of observations at 3 different HPLA radar facilities. Resolute Bay Incoherent Scatter Radar near the North Pole, Millstone Hill Observatory in Massachusetts, and Jicamarca Radio Observatory at Lima, Peru, near the equator. And every facility has its own quirks. So RISER-N and MHO operate in UHF, whereas JRO in VHF. Each one uses different pulse codes. MHO is kind of the odd one out in the Barker 7 for this experiment. They can transmit many different pulse codes, and then the other 2 use minimum side lobe 51 codes. And then they all have similar pulse length and pulse period, but couldn't quite match them up due to just reasons that I won't get into for the sake of time. But point is, in order to train a machine learning method, we have to tailor it to the specific facility. So we will use a pretty standard convolutional neural network architecture. What I do want to point out is that raw data is being passed into the neural network. It is a complex 2D in-phase and quadrature IQ raw data array. We're not doing any pre-processing on it, which greatly improves the computational efficiency of this method. There are 3 convolutional layers, which help pull out the features that you'd expect to see in the head echo. And then the neural network will output the probability that an image contains a head echo. And then if that probability is greater than 1/2, we then have classified that image as containing a head echo. And also, these RTI images tend to be rather large, larger than just the 150 by 150 input that I showed on the prior slide. And so we split them up into basically 150 by 150 image segments with a little bit of overlap at the edges. That helps us make sure that we're detecting any short duration head echoes near the edges and not missing them because we cut the image right there. Then we classify each segment as either a head echo containing a head echo which has the label of 1 or not, and then label of 0. Trails in this case give us a label of 0 since we're not explicitly looking for them for this research. Then we can group together adjacent positively classified segments for further analysis, determine the meteor's altitude, range rate, and other properties. So in order to train the neural networks quickly and efficiently without lots of manual labeling, we use physics-driven synthetic data. So what we do in order to generate these kind of fake head echoes or synthetic head echoes is we assume that the head echo's range decreases via an exponential because as the meteor enters Earth's atmosphere, the density will increase as an exponential. So that's the dynamics we would expect. We have some random parameters, the initial range, velocity, and acceleration. And these will be randomly chosen within the range for your particular head echo. And then the received voltage signal will be a result of multiple physical factors that you get with the reflection. And so the first term here is just the overall signal strength. How bright is the head echo? Then you have your pulse code, obviously, because it's being reflected. Then you'll have a Doppler shift because it's moving towards the facility. And then there will be a term due to motion through the radar beam. So it'll like start off dim, then get brighter, and then presumably get dim again. And so we assume that that takes the form of a sink. This is a rather large assumption, neglects a lot of the physics. However, for a neural network, we just want to train it and have like a ballpark head echo or something that looks close to it that then it will detect similar objects in the real data. So that is good enough for what we're trying to do here. It is also important to note that head echoes don't just exist on their own in a vacuum. There are other phenomena or noise that will occur at every facility, such as sporadic E events, equatorial electrojet, non-specular trails. They all have very high SNR and tend to be very pervasive. So we can actually identify these in the data much more quickly than we could label the head echoes. So that takes a few hours to get a few thousand of them if you look through RTIs using kind of a Python program that I wrote. And then you can play some games with that to artificially increase the number of those examples from, say, 2,000 to 20,000, linear combinations, vertical translations, horizontal, et cetera. And so you can combine the synthetic head echoes on their own with no noise with, say, equatorial electrojet at Hikamarka or something else and background noise to get your training segment that the neural network will see during training. And then just for visualization purposes, if you took a match filter on this, then you'd more clearly see the head echo streak, but that's not what the neural network is seeing. This is just for visualization here. Also, for each training example, we include a version without that synthetic head echo, and then that has a label of 0, and this helps the neural network learn to discriminate between examples that contain a head echo and examples that do not. Sometimes the head echoes will be in the corner of the example, or they will just be very weak. So here I'll show a video of how the CNN is making its decision. And so when I click play, what's going to happen is there's going to be a contour plot that shows how the CNN is making its decision or what parts of the image it is considering important in making its decision. These can be obtained by using some tricks with the neural network architecture that I don't have time to get into, but it's pretty cool how it works. And so when I click play, this is as the neural network is training, it focuses less and less on the noise and more on the head echo right there. Then at Hikamarka, now we'll have a non-specular trail as well. You can see initially that the CNN thinks that the trail might be part of the signal it's looking for because it's just looking for any high signal event, but as we train it, less and less does it care about the trail and more it cares about the head echo, which is what we would expect. So we know that the neural network is doing the right thing now. It is detecting what we would expect it to. Now let's look at the performance metrics at each facility. So we have 3 facilities, and then at Hikamarka we're actually having 2 test sets, one without the equatorial electrojet present before dawn, and then one with the equatorial electrojet present kind of during dawn. And so what we find is that it's overall very accurate. And I should also point out that these test sets have thousands of examples in them with about 100 or a few hundred that do contain head echoes. Accuracy overall is above 96% across the board, which is good, means CNN is generally classifying segments correctly. Sensitivity is across 70% across the board, and this means that a majority of the head echoes that are in our data are being identified. So at least 70%, if not more, because we're breaking it up into chunks. And precision is above 50% across the board, specifically 50% when the equatorial electrojet is present. It goes up from there to 66% when it is not present, and then up even higher at Riser N and Millstone, which tend to observe fewer other signals besides head echoes. This is still good because false positives can be quickly rejected, which precision is a metric of how many false positives you have. If it's lower, there's more. And in future work, we'll also work to continue improving this metric. What we can also do is we've analyzed all of the head echoes in 2 of our test sets at Riser N and JRO to determine all of the head echoes' range rate and altitude. And also then we have different labels on these scatter plots depending on whether or not the neural network detected them. Circle if it was detected and a triangle if not. What we see is that the only observation bias of our method from this plot is that weaker head echoes do tend to be missed more often, but you can also see that there's not very many triangles in these plots, which is good. We're detecting most of the head echoes. And most of the head echoes that are above 15 dB are being detected, and there's no other significant observation biases in, say, altitude or range rate. And so our method is not adding any biases beyond the observation biases of the radars themselves, because radars are complicated. They might observe, for example, fewer low altitude and low range rate meteors, but it's good that our method is not then another factor we have to account for if we're trying to do some sort of a population analysis at our facility. All right, so to wrap up, the biggest kind of impact of this work is that the synthetic head echo technique and using this synthetic data to train our neural network greatly speeds up all of the more scientific goals of the work because then we have like a list of all the head echoes that are in our data that's just automated, and then we can feed those into an analysis program, and then that allows us to learn more about these particles themselves that are entering Earth's atmosphere. this can also be applied to any experiment. So say I want to do a new head echo experiment tomorrow at, say, like a different facility besides these three, then we could very quickly take what comes out of the data, or even possibly in real time, get a list of the head echoes and then do an analysis on them, which has not been done in the past. Overall, we trained a CNN with this method with synthetic data. We got more than 70% of the head echoes identified in the real data at 3 facilities. So good performance across the board. CNN more reliably detects stronger head echoes, but many weaker ones are also detected. In the future, the technique will be extended to more complex neural network architectures and return bounding boxes that are more accurate around the head echoes, and also can be integrated with the prior work and their architectures. And then just in general, because this method allows us to quickly identify head echoes, which allow us to learn a lot about these particles directly that are entering Earth's atmosphere. This will advance the general science goals that we get through head echoes, including improved estimation of meteoroid properties and their origins, and then what dangers they pose to spacecraft. Thank you very much.
Questions?
So your current method right now uses 1,000 times more power. You're using megawatts of power versus the synthetic. The other one, the specular antenna or radar, use kilowatts. What makes your method more advantageous that will allow you to be able to use more power? Like you're using more power, more resources. What advantage does it provide than the specular radar did?
So that comes down to the facility that we're using. I would say that head echoes in particular cannot be observed, or they're starting to be able to be observed using kind of modified instruments that were initially specular meteor radars, but then were turned into something that directs more of the power directly up versus all sky. That's not so much related to the method that I'm presenting. That's just if you have a big radar facility, it'll observe more of these radar signatures, including the head echoes. Does that answer your question? Awesome.
Go ahead.
So with your structure for your neural net, would you expect improvement if you also included real data into the training mechanism, or is that a kind of a product of your structure that you need the synthetic one?
So we could absolutely, one thing I was thinking about is we could use this method with just purely synthetic head echoes to then detect examples that contain real head echoes and then incorporate them into our training set. So that's something I'm going to try going forward in the future. My guess is it would improve sensitivity and precision metrics by a little bit. There are other things I would also want to do in future work, though, to also improve those metrics that I think would make a big difference.
Yeah, go ahead.
Hi. When you generate your data set, I know that you combine your synthetic data, like head echoes, with the ground traffic, right? And the magnitude of the signal to the traffic should be very important. I want to know how did you control the magnitude ratio?
I see. So you're asking, say you have a synthetic head echo that is very weak, and then, say, electrojet that's very strong, then you could have a situation, and this is something I accounted for, where if there is a synthetic head echo that is weak and I add it, it could be that the example should be negative, because if your electrojet is just so strong that it completely blocks out your head echo, like even if you're looking very carefully with a human eye at the data, you wouldn't see a head echo. That should be a negative example. So actually, when combining those examples, I made sure, just to make sure that the power of the synthetic head echo was at least some ratio such that when you use a match filter or that decoding, you would definitely see the head echo.
Last question. Go ahead.
I'm curious about, have you tested this model with data it hasn't seen from other sites, and how did you do training, testing, validation split just in your model training?
Yeah, so I'm purely, and let me know if this is answering your question or not, I'm purely using synthetic data to train the network, so there's no split between, say, you have this much data that we're using to train and this much to test. It's very fast to just generate the synthetic data, and then we're testing on the real data, which makes sure that it is detecting the right thing. Does that answer your question? Or?
Yeah, it does.
Okay.
Thank you so much.
All right, thank you very much.
Are we live? Is it good? Okay. So let's just... Okay, hi everyone. My name is Duncan Madden. I'm from the University of Michigan, and I'm excited to tell you about the work that I've been doing on in situ calibration of antenna arrays using SAR imaging. So I'd like to talk a little bit about why phase array calibrations are necessary. So I have here examples of two radiation patterns. One is sort of a clean radiation pattern, and the other is a radiation pattern where numerous errors have affected the weights on each element, and the effect is that your main beam's gain is reduced, side lobe levels come up, and your beam shape is sort of distorted. So the goal of an array calibration is to determine what these errors are and then correct for them. So I'll talk about what some of the sources of error actually are. So some sources of error: mutual coupling between elements, uncertainty or shifts in element positions, component aging or component sensitivity to temperature, and multipath effects, like the effects of nearby scatterers or platform mounting effects. So calibrating for all of these effects simultaneously is already a difficult problem, and this becomes even more challenging if you're in a quickly changing environment where all of these different sources of error are changing temporally. So the class of in situ calibrations has the goal of calibrating on the fly or online without the ability to return to a stable environment like your lab or your factory. And this is particularly important when you're in a transient environment or when you have an array mounted on something like aircraft or spacecraft where the array is not accessible to retrieve and do additional calibration testing on. So in situ calibration has been studied for some time, and generally these calibration methods can be divided into two different classes. One is a group of external calibration methods where you use something like an antenna in the far field or a calibration target in the far field, and you use that calibration target to determine differences in the element transmitter or receiver paths. So this approach is very accurate because the external calibration target propagating to that and returning it includes all of the effects inside of the array and outside of the array. However, the downside of these calibration methods are that you need a target in a known location beforehand, and it's difficult to find these, among a clutter, strong scattering targets among clutter, or without having them strategically placed. Now, internal calibration methods calibrate for antenna effects beforehand, and then use something like mutual coupling between antennas or self-sampling circuitry to determine changes in the transmit and receive module errors. So these are also very convenient. However, they're usually limited by some geometrical constraints, and additionally, they can only calibrate for the TR module errors. So it seems like there's still sort of an open problem here for in situ calibration in the development of a method that doesn't require additional equipment or strong calibration targets with known locations and can be used in situ, but at the same time includes all of the decohering effects and can work for any array shape. So we have a proposed solution for this problem, specifically for the case of arrays mounted on aircraft and spacecraft, where you have access to the transmit and receive signals for each element. So what we're proposing to do is to use actually the ground below your craft as your calibration target, and then to use SAR imaging to reduce that image into an image, or sorry, reduce that scene into an image of many pixels, and then use the individual pixels as calibration targets. So let me talk a little bit about why we need to use SAR in this case. So without SAR imaging, you have sort of the spot beam on the ground, and the return signal comes from within that entire beam area. And when you look at this element to element, you compare element to element, each element would see sort of a different phase center for this one scene, right? And so you wouldn't be able to use that data to discriminate between differences, amplitude or phase differences in the transmit or receive channels. But with SAR imaging, you can use the velocity of the aircraft or spacecraft to sort of create a synthetic array with your antenna element in multiple positions, and you can do imaging with that, where now you reduce the extent of this target down to 1 pixel, where the size of your pixel is determined by your range resolution and your cross-range resolution. And in fact, you can form many pixels within your image, where images fall within pixels fall within sort of different parts of the beam, and you can then average over these many pixels to reduce the effects of system noise. And you would have perhaps hundreds of thousands or millions of pixels in your image, and averaging over them, you can significantly reduce that effect and get a very accurate calibration value. So a bit more about the logistics of how the calibration would work with a general target. So consider a case where you transmit from one element, and then you receive that return signal from your target simultaneously at all of the elements. Now, you have, in this case, 4 received signals, and the difference between each of these received signals is due to the receiver of each element, right? They share this common transmitter, and then there are geometrical effects like where the antennas are located, which if you know that to some accuracy beforehand, then when you compare the signal that was received at, say, antenna 1 to antenna 2, you can determine the differences in the received channel, relative in antenna 2 to antenna 1. You could repeat this for each of the elements so that you can calibrate or you can determine channel imbalances with respect to one element that you choose as your sort of reference. Now, in the transmit case, you could transmit simultaneously from each of the elements and then receive the signal at one individual element. And you could do this simultaneously if you use orthogonal codes in each of your transmitted signals, and at the receiver, those can be sort of divided and identify which element they came from. So in this case, you would be, the difference between each signal would be in the transmitters because they share a common receiver. So that was for sort of a general target. How would you use a SAR image? So again, consider a case where you have you transmit from, we'll call it antenna 1, and you receive at antenna 1, and you form your image from that data, and then you do the same thing. You receive at antenna 2, and again, you form an image. Now, you co-register the images, and you compare pixel to pixel amplitude and phase differences. So these amplitude and phase differences are the receive channel imbalances. And you can form actually a difference image, a phase difference image or amplitude difference image for all of the pixels within, between the two images that you generated. Now, because of the added system noise, the estimation value that you have for each of the pixels in this difference image, it's going to vary, right? Because you're going to have some added error to it. And at the same time, the ground target that you're looking at, if it's a random rough distributed target, is also going to have some variation in the strength from which direction you're looking. So some of the pixels are going to have higher strength than the noise floor, and others will have signal levels that fall below the noise floor. So if you select the pixels that are SNR greater than 1, and you use those and eliminate the other pixels and average over the many pixels that you have left, then you can significantly reduce system noise just through averaging. So we've conducted some initial validation experiments as a proof of concept that we can indeed measure channel imbalances using SAR imaging with the method proposed. So the experimental setup that we used, we had 2 antennas where we transmitted from one antenna and received at the same antenna. And we rotated a rough surface target to create an inverse synthetic aperture radar imaging scenario. Similarly, we transmitted from antenna 1 and we received at antenna 2. And from this, we generate two images, which we'll call our S11 image and our S21 image. And from those two images, you can generate your phase difference image and amplitude difference image, where the pixels in those images should be some estimation of your channel imbalances. Then, so that first case sort of is going to act as our baseline channel imbalance experiment. And then we repeated the experiment, adding a known change to one of the two receiver paths. And what we did, we just inserted a 3 dB attenuator that we were able to measure its insertion loss and insertion phase separately. And then we repeat the experiment. And again, we generate another phase difference and amplitude difference image for this, from this S11 and S21 set of data, image set of data. And then, using those two difference images, we can compare the estimated values of channel imbalances before and after the known change was introduced. And what we expect to see is that the change in estimated phase difference and amplitude ratio should match the known perturbation. So a bit more of the nitty-gritty details about our setup. We used two X-band horn antennas that were each about 1 meter long, over 3 gigahertz of bandwidth, 401 points in a stepped frequency setup, and our system had range resolution of about 5 centimeters and cross-range resolution of 10 centimeters. So you can see here the two antennas, and then looking downrange, you can see that rough surface target that was rotated. So we actually performed this experiment with two targets. Our first target was just a fiducial target, which I'll talk a little bit more about later. There was 3 vertical metallic cylinders, and then a random surface that was made by gluing a bunch of rocks to a large circle of styrofoam and then spraying it with conductive paint. So the fiducial target, the point of that was to just ensure that our imaging setup was operating as we expected it to before we moved on to the more difficult calibration task. And so you can see 3 distinct peaks here in an amplitude response image corresponding to the 3 peaks for the different cylinders. So this is also an amplitude response image. This is the S11 amplitude response image taken by transmitting and receiving from the same antenna. We also formed similarly a S21 or bistatic image, and then the goal is to take that S11 image, compare pixel to pixel to the S21 image to form a difference image in amplitude and phase, use that as our baseline, and then try to see if we can detect a change, right, from that baseline. So here you're seeing the phase difference image with the baseline. And then below this is the phase difference image, so comparing S11 image to S21 image after we've added this known change. And what I want you to notice is that there is a very clear shift in color here that corresponds to a change in the mean phase difference. Similarly, these are amplitude ratio images, and again, you can see that there is a change in the mean amplitude ratio of the many pixels within this image. Maybe a more clear way to see exactly that there is, some mean value or some value that these pixels in the difference image is concentrated around is to look at them in histogram form. So maybe if you look at the phase difference histograms down here, so we have a histogram of the for each pixel in the baseline phase difference image, what value each pixel had, right? What value each pixel estimated for our channel imbalances. And you can see that, yeah, you have values all the way out to, 100 degrees here. This is cut off. It goes all the way to 180 and in the other direction. But it's very concentrated about some centroid. And when we add the known change, the distribution shifts to the left, and that corresponds to a change in mean. And so the actual change in mean was about minus 55 degrees, or the estimated change was about minus 55 degrees, and the actual change that we measured for the attenuator in isolation average over the frequency bandwidth was minus 54 degrees. So I think this shows that we were able to extract those changes to the channel imbalances. Similar, we had also for the amplitude ratio estimation, we had similarly, similarly close results. So one issue that, that may come up is that if you have lots of phase variation over your frequency band, when you perform the imaging step, everything is compressed to one data point, and you aren't able to extract that variation over frequency. So we've looked at another calibration process, wideband calibration process, where you process over sections of the band to generate multiple values at different frequencies and then interpolate between them. So I just want to recap some of the advantages of this. You can calibrate at any given time using the terrain below with no additional equipment, accurately with diverse array layouts, all elements simultaneously, and you can reduce the effects of noise by averaging over thousands of calibration targets. So I think that we've introduced sort of a new possibility for calibration, a new source that could be used in calibration methods for these in situ approaches. So we've done some additional work that I didn't have time to talk about now, but it seems like I'm running out of time, so I will just end it here. Thank you.
Questions? Go ahead.
Nice talk. On slide 34, you show the change to, or the histogram for the change due to your 3dB attenuator.
Right.
And you can clearly see the 3dB change and the phase change, but why does the histogram spread out?
Yeah, that's a very good question. So, in fact, the accuracy with which you can determine your channel imbalances is proportional to your SNR, right? So if you have higher SNR, then this distribution is going to be more tightly distributed, right? And as SNR decreases, it's going to spread out. And we've actually looked at matching distributions, theoretical distributions, phase difference distributions to these histograms. And also we've looked at, based on SNR, what phase accuracy can you actually expect to extract. So yeah, that's exactly what's happening here. The signal has gone down in the second case by 3 dB, so the histogram has spread out.
Thank you.
Mm-hmm.
Go ahead.
Does this strictly require that the transmit element actually be one of the array elements, or is this also solvable for like incidental signal that happens to be near frequency band scattering and being received?
I think that if you were, so in that case, maybe if you were trying to calibrate all of the receivers in an array and you had a separate transmit element that was not part of the array, yeah, you could do that similarly. Each of the receivers would have the same common transmitter. Yeah.
Will your system have to actually go down from its operation to be able to do a calibration, and if so, how long is that downtime?
Yeah, so it depends on the system. So I mentioned before that we've looked at SNR, and SNR can be calculated or estimated based on your system parameters, like the velocity of your vehicle, bandwidth, things like that. And one of the parameters that factors into your signal-to-noise ratio is your coherence time, the amount of time that you're actually looking down to form your image, right? That determines the signal-to-noise ratio of your image. So you can use different values of coherence time and estimate what SNR I'm going to get. So it may vary depending on the system. Some systems may need a longer coherence time, some may need a shorter coherence time.
Last question.
Is the array well calibrated after one imaging, or do you need to take several sets of images to kind of innovate this process?
So what we've done right now is just with one set of images. I'm sure that if you wanted to improve I guess that would expand your data set. It would give you more data points to average over, so I would expect that it would improve the accuracy, but so far we've only looked at single look. Yeah.
Thank you.